Greetings everyone. This is the free response question number 4 from 2018 for both the AB and BC exams. Let's take a look. So here's the prompt, here's the question. It's one of their classic tabular examples. So they're going to give you a table and they're going to ask you to do some analysis based on the table. And so you can expect to be doing average rates of change to approximate instantaneous rates of change. Sometimes they give you intermediate value theorem, mean value theorem can come up, and then they're going to try to connect it to a table, to an actual function at some point. Also, those are typically some of the things they do, and some Riemann sums, right hand, left hand, or trapezoids. You're going to see some of that stuff here. So these are some of the common things that you'll see. So pause the video, go try it, see what you can come up with, and then come back and see how you did. So it says the height of the tree at time t is given by a twice differentiable function. Twice differentiable is good to know that right there. I don't know why I'm using that type of right there. That looks better. H of t is measured in meters and t is measured in years. And then selected values of h in the table. It says use the data in the table to estimate h prime of 6, and then using correct units interpret the meaning of h prime of c in the context of the problem. So make sure you mention what's going on here. Don't give a graphical interpretation. Don't say it's the slope of this or that. Give it in terms of the problem here. So we want h prime of 6, and so we get to go to the table and figure out where 6 is, and obviously I hope 6 is somewhere between 5 and 7. And so we're going to do the average rate of change on the interval from 5 to 7 to get an approximation for h prime of 6. So h prime of 6, we've literally been doing this since day 1. So, and you did this in pre-cal. It should not be a big deal for you to figure this out. Sorry, my technology is messing with me a little. Over 7 minus 5. Excuse the sloppiness a little bit. I don't remember the values. So h of 7 is 11. H of 5 is 6. So 11 minus 6 in the numerator over 2. And that is going to be 5 halves. And so now how are we going to interpret this? Now, a couple things on the interpretation. Notice that they say using correct units. So we have to mention the 6. 6 is the number of years, and then we need the units on h prime. The units on h is measured in meters, okay? And so when we take its derivative, we're going to have meters divided by years over here for the input variable. It's always the units of the output divided by the units of the input. So those are some of the things. So again, h is the height of the tree. And so h prime would be, we can interpret this to see, at t equals 6 years, the height of the tree is increasing, excuse the sloppiness, these pens don't write very good, at a rate, they want to see the word rate here, of 5 over 2, I don't remember the units on h, meters per year, I think that's it actually. I ended that with the wrong tone, but at t equals 6 years, the height of the tree, my goodness, I said tree, never wrote tree, but the height of, this is sloppy, I apologize, it's late, I'm a little tired. The height of the tree is increasing at a rate of 5 over 2 meters per year. So notice that I used, the units on the years, so 6 years. I have the interpretation, it's the height of the tree is increasing at a rate, or you can say the rate of change of the height, that's another way. And I got the units, meters per year, on that 5 halves. So you need all those things. This is a 2-point question, 1 point for your estimate, the 5 halves, and 1 point for the interpretation with proper units. Let's go back to the prompt over here. So in part B it says explain why there must be at least one time t between 2 and 10, exclusive, such that h prime of t is equal to 2. Now here with this one here, with this, you're going to want to, there's a connection that implies a certain theorem that we have, one of our abbreviated theorems, and that connection comes from this. We want information about the derivative, h prime. We were given information about the function itself. So what theorem do we have what is the theorem that we have that connects the derivative and the function itself in some way? Well, hopefully it comes to mind the mean value theorem, because that's what we're going to use here. We need the function to be continuous on the closed interval, differentiable on the open, and we were told it was twice differentiable, so we have continuity from there, and we're going to want to mention all those things. But what we're trying to show is that for the mean value theorem, that the instantaneous rate of change, I'll use the function notation here, so it's h that we're talking about. The instantaneous rate of change of the function h at some value c is going to be equal to the average rate of change on the interval. I believe it's from 2 to 10, so h of 10 minus h of 2 over 10 minus 2. So there's going to be some value c between 2 and 10, okay, such that h prime of c is equal to the average rate of change over the entire interval. And so we're going to go sit there and figure out this average rate of change on the right-hand side. So we were going from 10 to 2, and so 15 minus 1.5 is going to be the numerator here. And then divided by 8. And so that's going to be, what is that, 13.5 over 8. And I even forgot the question here. Explain why there must be at least one time where h prime is equal to 2. Well, we didn't get 2 there, so maybe, let me go check my numbers here one more time and see if I went wrong somewhere. No, my numbers are correct. So obviously the interval isn't the entire interval from 2 to 10. So I'm going to go back and look at the table and see if I can figure out some interval where the average rate of change is 2, so that I can get what I'm looking for here. And so let's see. If I look on this interval here, if I look between 3 and 5, the increase in the outputs are by 4 and the inputs by 2. So that would have an average rate of change of 2. So h prime of c is going to be equal to, h of 5 minus h of 3 over 5 minus 3. We said that was going to be 6 minus 2 over 5 minus 3, 4 over 2, which is 2. So we have it. And notice the interval 3 to 5 is inside the interval from 2 to 10. So the first attempt didn't work, but we went and found another interval on which this did. So then we just write the argument. So since h is, it looks like his, but that's h is differentiable, h is continuous, so by the mean value theorem, you may want to write out mean value theorem instead of abbreviating it. There is a c in the open interval from 3 to 5 such that h prime of c is equal to 2. Alright, so we got it. Okay, let's move on to part C. Now part C has us, what does it say? Use a trapezoidal sum with 4 subintervals indicated by the data in the table. This means we don't use the same delta x. This means that we have to use the data indicated by the table. So we use the widths according to each subinterval. So my first subinterval is going to have a width of 1, then it's going to be 2, then it's 2 again, and then it's going to be 3. So those are all the widths that we have over those subintervals. And we're trying to approximate the average height of the tree. So we need our average value integral. And so, I'm sorry, we're going from 2 to 10. And so we're going to need 1 over 10 minus 2, integral from 2 to 10 of h of t dt. So that's what we want to approximate that with the trapezoids. Okay, so I'm going to need 1 over 10 minus 2, and then I'm going to need some trapezoids. Okay, so the first interval goes, the two bases are going to be the 2 and the 1.5 right here. So it's going to be 1.5 plus 2 times the height, which on the first interval is 1 divided by 2. And the next one is going to be 2 plus 6. Let me see if I can remember this. 6, 11, 15. And then we went 1, 2, 2, 3. 6, 11, 15, 1, 2, 2, 3. Okay. 6. This was the height of 2 over 2. And then 6 plus 11, the next two heights, times 2 divided by 2, plus 11 plus 15 times 3 divided by 2. And then from there, I mean, technically we don't need to do any more. We don't need to simplify because that is correct. I'm not leaving anything, any integrals unevaluated or anything, so we could stop there. I'm going to pause and do this calculation because I don't want the video to be longer than it needs to be. Alright, the numbers are kind of ugly. Again, you don't have to simplify this big old mess up here. You can leave this big old mess, whoops, this part right here, you can leave this stuff alone. That is correct. We don't have to do anything else. Okay, let's go on to part D. And then lastly, part D says the height of a tree in meters can be modeled by a function g given by g of x is equal to 100x over 1 plus x, where x is the diameter of the base of the tree in meters. When the tree is 50 meters tall, the diameter of the base of the tree is increasing at a rate of 0.03 meter per year. According to this model, what is the rate of change of the height of the tree with respect to time in meters per years at the time when the tree is 50 meters tall? Alright, so we got to figure out some things here. We got to figure out when the tree is 50 meters tall, so I need to set g equal to 50 meters. Let me change to a darker one. So I need g of x equal to 50, and that implies very quickly that x is going to be equal to 1 because, well, look at it. When you plug in 1, you get 50. Okay. Now we have to differentiate with respect to time g of x. Okay. So notice that the t and the x are different. So we have to use the chain rule. And if we don't use the chain rule here, well, we're not going to get this right. So we're going to get g prime of x times dx over dt. Now, if you remember in the problem, they told us that dx over dt, the rate of change of the diameter of the tree, is increasing at 0.03. So that gets a positive 0.03 meters per year. Okay, so we know what that is. To get the derivative of g prime, we're going to have to do the quotient rule. I got this written off to the side, but I'm going to pause the video. Try to keep this under 15 minutes. Alright, so I wrote out what we get by the quotient rule. Notice that when I did the quotient rule that I'm factoring out the dx over dt. There should be a factor of dx over dt from each term in the numerator here. I just factored it out so I could put it at the end. It's legitimate algebra. I know some of you get nervous about algebra, but it goes there. Okay. Remember, we're going to use this value over here. We're going to plug in 1 for x. So at x equals 1, and I'm running out of space and time. When you evaluate this, you're going to get this to be equal to 3/4. Just plug in 1, plug in 0.03, and simplify if you'd like. Okay. I'm just checking the problem here to see. We don't need to explain anything. This is a 3-point problem. 2 points for getting the derivative with respect to t of g of x. 1 point for the answer. And in the notes for this problem, it says you only get 1 point out of 3 if you do not use the chain rule. So you have to use the chain rule in order to get this correct. Obviously, it's not going to be right if you don't use the chain rule, but so they want to see that you understand that concept. All right, ladies and gentlemen, I hope that made sense. Go study.